Welcome everyone to the 6th edition of the Vacuum Transport Seminars. Today we have two interesting talks from the student team U0 from Stuttgart and from Tom Boring from the Technical University of Munich. So without further ado, I would hand over the word to Andrea, who is going to present the first speaker of today.
Yeah, thank you, Daniel. So yeah, exactly. Our first speaker today is Marius. He's from U0. U0 is a student team, just like Swissloop, who is building prototypes and participating in student competitions like the European Hyperloop Week. And actually, U0 is quite a young team. I think it's only the third season this season, but they've already been quite successful last year, since they won 3 out of 7 awards, which was really great to see as such a young team. And yeah, so Marius was the leader of the aerodynamics team last year, and that's also the topic he's gonna present to us today. So he brought a study with him about drag savings and the energy efficiency in a low environment. And basically, he will present to us his findings in this study. So with that, I would say the stage is yours and you can share your screen. I'm looking forward to the presentation, Marius.
Yes, so thank you very much, Andrea and Daniel, for the introduction. And yeah, I think you should see my screen now. So again, thank you very much. As already mentioned, I'm a former aerodynamics lead from U0 Hyperloop in season 2021 until 22. And so today I'd like to share with you the key results of our research study, which we, by the way, also presented last year at the HW. And the research focuses on drag savings and energy efficiency of the low pressure system in Hyperloop. Yeah, for the calculations, we used a lot of computational fluid dynamics simulations. And yeah, so I'd like to start with our research goals. So first of all, we asked ourselves how much energy Hyperloop transport system consumes in total. Because during our research, we kind of realized that there hasn't really been a bird's eye view onto the complete system. And in addition, we want to gain more knowledge about the parameters in the system. And also we want to know their influence, because that will help us later in our third step, which is the optimization, where we want to minimize the required energy of a Hyperloop system. So let me just briefly touch on our concept. So in order to compute the different pairs of energy, so like the energy needed for propulsion, for levitation, or also the generation of a vacuum, we're using analytical equations. And in particular for the propulsion, it is necessary to know the aerodynamic drag forces. And therefore we created a CFD framework, which consists of a parameter space, sampling methods, the simulation itself, and also a surrogate model. I will explain that a little bit later. And in the end, we are able to perform a sensitivity analysis, and we can also optimize then the energy. I touched on the different shares, and here I'd like to go a little bit further. So you can see for a tube, for example, we need to, first of all, produce the vacuum, and then we have to maintain it. So because for certain materials like concrete, for example, there is constant permeation in the material, so that the air is constantly coming into the tube, and so we have losses. We have also losses at at linking points of different tube segments. So at joint sections, we have leakage. And in addition, we have also losses at airlocks. From the pod side, we need, of course, we need energy to accelerate the pod, but we also need energy to maintain because we have the aerodynamic resistance. So we need energy for propulsion, but also energy, of course, for the levitation. What we didn't consider in this research work was the infrastructure part. So this could be an interesting topic maybe for the future. So as I said, for the propulsion system, we are assuming that the propulsion must compensate the aerodynamic drag. And therefore, we created a CFD model, as you can see on the bottom. You can see the Hyperloop pod in green, and it has a length of about 30 meters. And it's roughly long enough to carry around 50 passengers. And you can see in the front and at the back of the pod, we left enough space for the flow field to develop over the geometry. Concerning the diameter of the tube, we left that as a variable because we want to achieve different blockage ratios later on. And material-wise, we're doing a comparison between steel and concrete. Why steel and concrete? Well, both materials are quite common and also widely available on the market. Of course, in the future, you could also imagine other fancy materials, but out of simplicity, we are doing the research with steel and concrete. Of course, we are defining proper boundary conditions at the inlet and the outlet of the domain, so where the flow goes into the domain and where the flow goes out. And as you can see on the right-hand side, we are using a block structured mesh. And also because we have axis symmetry, we created a wedge model, basically one cell into the C direction. So when we have like those variable parameters like the pod Mach number, the blockage ratio, and tube pressure, we define specific ranges. So for the Mach number and the blockage ratio, we defined 0.2 until 0.6 as a range. And for the tube pressure, we are considering pressures between 10 and 1,000 pascals. Those values are mainly based on recent papers, but also based on the Kantorowicz limit, of course, which I will go further later on. So having those ranges defined, we can then develop a design of experiments to investigate 30 different parameter combinations. But instead of just creating random points in our design space, we are using the Latin hypercube sampling method. And with this method, you basically subdivide the space into smaller subspaces, and only one combination per subspace is allowed. So this avoids clustering versus a random method, but still the randomness is remained. And so we can basically then start with our simulations. In total, we ran over 30 RANS CFD simulations with OpenFOAM. This is an open source CFD software. And we are using the turbulence model K omega SST, which is widely available, or is quite a common model in the aerospace industry. Since we are exceeding the Kantorowicz limit in some cases, we want shock effects to develop and we want to allow them. So we're choosing a transient and also compressible solver. In addition, we're performing simulations to basically see if our modeling is correct. So we are doing a mesh conversion study. And so I want to briefly go into the results. In particular, I want to point out two specific results. And for that, on the left-hand side, you can see the blockage ratio over the pod velocity at around 1000 pascals. And you can see the blue curve, which is the Cantor width limit for each pod Mach number. And so let's consider, first of all, set point A, which lies slightly above the Cantor width limit. And you can see in the on the right-hand side that there is, of course, the pressure buildup in front of the pod. But you can also see that the velocity distribution along the pod is also quite continuous, and there are no shock effects because we are just slightly above the limit. Whereas when you consider set point B, which is a lot over the limit, as you can see, first of all, you can also see that the diameter of the tube shrank because the blockage ratio went up. And you can see that there are like shock waves appearing, especially at the end of the pod. And with that, with those shock waves, of course, your aerodynamic drag will rise a lot in comparison with A. Okay, so now we can basically assign the drag values to our simulation samples, as you can see on the left. But you can also see there are a lot of empty gaps between the points, so we want to fill them, and therefore we are interpolating between the points. So we're using a meta model, and so that in the end we have a continuous distribution of the aerodynamic drag over our design space. So you can see the result on the right-hand side, and so we have for any Mach number, blockage ratio, and tube pressure value, we have a specific drag. And yeah, with that, we are finally able to perform our energy analysis, which brings me to our key findings. So our sensitivity analysis shows that for a concrete tube, the energy consumption is highly sensitive for low pressures. That means that for a small variation of the pressure, the energy goes up by a lot. Whereas for the steel tube, we found out that the frequency of the Hyperloop capsules is important. So it really matters if the pod departs like every 10 minutes from the station or every 4 minutes. And you can also see that in the diagram on the right, that the frequency is here really important. In our optimization later on, we found our, let's say, best case values for Mach number, blockage ratio, and pressure. And I want to point out the blockage ratio right here because it's at the upper limit with 0.6. And that really tells us that we should reduce the diameter of the tube as much as possible so that we can minimize also the energy needed for the vacuum generation. And we also found out that a steel tube is to be preferred because we have a yearly consumption of energy of about 33 gigawatt hour, per year and per 1,000 kilometer tube. And this, when you compare it with concrete, the value is doubled. So we really prefer steel here. And if you want to put that into perspective, 33 gigawatt hour is like the energy production of 4 medium-sized wind turbines, if you want to say. So just to get a little feel of the consumption of 1,000 kilometer of our tube. Okay, and last but not least, like when broken down to all of the different shares of energy, we find out that the levitation takes the largest share with around 38%. And in the end, we also compared our values with other transportation concepts. So on this diagram, we have on the vertical axis the energy consumption in watt-hour per seat and kilometer. And in red, and the red bars are like our optimized values for steel and for concrete. In blue, we have the energy consumption from the Hyperloop white paper from Elon Musk proclaimed. And in yellow and green, we just took those papers for the values just to get like a better comparison. And you can really see the advantage of the Hyperloop concept when you compare the values with the values of a car and a plane. When you compare the red bars to the blue bars, you can really see the advantage. But what you also can see is that compared to high-speed trains like the ICE in Germany or the Transrapid, so the green bars on the right, you can see that the difference is not that high. And we are assuming that the reason for that is that the seat capacity of high-speed trains are a lot higher than what we took. So we took like 50 passengers per Hyperloop train, and if you compare it with high-speed trains, the passenger, you can like have 200, 300 passengers per train. So it makes makes a huge difference in our opinion. Also interesting here is the value that Elon Musk proclaimed in his paper with 25 watt-hour per seat and kilometer. So this value, interestingly, is also in our range what we calculated, which is quite interesting here. Okay, so what can we imagine doing further? Well, what we didn't consider in this work was the efficiencies and losses of the propulsion and levitation system. And we also didn't consider the efficiency of the pumps, which is, I think, a big point. Also, considering enhanced simulations in the future, maybe in 3 dimensions, when you can basically have like shock waves more in detail, it could be really beneficial. And also when you take velocity profiles for the acceleration from actual routes. So because we took like a standard velocity profile for the acceleration, but we think when you really take real profiles from actual routes, this could be also really beneficial. Okay, and with that, I'm at the end of my presentation. Thank you very much for your attention, and I'm looking forward for your questions. Thank you.
Yeah, thank you, Marius, for the presentation. And I have some questions for you. Maybe we start with like there's some questions regarding like the concrete and the steel tubes. So one question was, what type of concrete did you consider? And there's a bit more specific, like for example, ultra high performance concrete is very airtight, but is more expensive than conventional concrete. Have you taken the types of concrete into account?
Good question. To be honest, we used Darcy's law for the calculation, how much air is basically coming into the tube. But I'm not quite familiar with the exact material. So I just know that we used just one material for the calculations, but I cannot say in specific which type of concrete we are using here, unfortunately.
Okay, yeah. Also there, another question was, you talked about like different scenarios where, for example, I think you said steel is more sensitive to frequencies. Is there maybe also a scenario where concrete tubes would be beneficial?
Sure. I mean, if the so the big problem with concrete, as I said, was the permeation issue, because that was a large effect in our calculations. And I think from my perspective, as far as we saw the solutions and the results of the energy, I would say that steel was the only option for us. But if maybe there are other materials, other properties of concrete that could change. But that was really the big disadvantage we discovered.
Okay, yeah. So in your scenario, steel was basically the only choice.
Yeah, so maybe to also pinpoint it, it was, I think, half of the energy consumption of concrete with, I think, 33 gigawatt hour per year.
Mm-hmm. Yeah, there was also one question regarding that number, like that 33 gigawatt hours per year. What type of operation and maintenance does that cover or include?
Yeah, as far as I know, we didn't cover maintenance because that was a topic related to the infrastructure, which we didn't consider. And we are assuming the pumps are running at nominal conditions, so no specific cases of like specific scenarios. So it was just a rather conservative assumption here.
Okay. And maybe also like regarding the frequencies of the capsules, what was the range of the frequencies you've analyzed? And also maybe at what velocities, like also different velocities?
So the frequency was, as far as I know, around 150 to, I think, 700 journeys per day, I think. And concerning the speed, since we had the upper limit of 0.6 for our experiment, the optimal speed was at a Mach number of 0.5. So only half the speed of sound, put it that way. So not that high, but still in the upper range of our consideration. So I would say if we extend the range to higher Mach numbers, the optimal Mach number would also like tend towards the maximum.
Okay. And also regarding that, how does the energy consumption vary with like different frequencies and different speed?
Good question. I'm not quite sure about that, because the frequency was just in our sensitivity analysis, and then we set the frequency to a constant in our later considerations when we calculated the energy. So this is, to be honest, the point where we could do maybe something in the future, because we took, I think, the lowest frequency value for our energy calculation. So the 33 gigawatt hour per year is the value for, I would say, the lowest frequency we considered.
Okay, so you haven't compared those two in your energy consumption?
Yeah, that's a topic we didn't cover.
Okay, and then maybe also one other question, like, did you also consider different shapes for your simulations? Because like you've been talking about, for example, different blockage ratios, so the tube dimensions differed. Did you also try different like capsule shapes?
Yeah, in the beginning it was actually a thing which we thought about, but in the end, also due to computational resources, we kept the simplified shape like we saw it in the presentation. Yeah, as I said, we basically changed the diameter of the tube so that we can achieve different blockage ratios. And so, yeah, unfortunately, we didn't cover the shape aspect, but also maybe interesting maybe for the future to see what kind of shapes are beneficial for different velocity ranges, for example.
Mm-hmm. Yeah, I because I think that would also probably make it different for the whole fluid simulations. Then maybe one also personal questions. Like you also took like the acceleration, the propulsion, and the levitation energy into account, right?
Yes.
what kind of concepts did you think of in these, like what motor or levitation system?
Yeah, so we took the EDS system for the levitation, and we took the values for the consumption from a recent paper. Cannot really tell you the name of the paper, but it was definitely the EDS system. But yeah, of course, there is a lot of research going on that topic. But yeah, out of simplicity, we took one value for the EDS system.
Mm-hmm. Okay, nice. And then maybe as a last question, is your thesis publicly available?
As far as I know, not yet. But if someone is interested into the topic, I'm of course happy to share it. And I think that should be no problem.
Okay, nice. So if any
So
other questions,
just contact me,
yeah.
maybe over LinkedIn or wherever. So yeah, or over MuZero if you want. So I think that should be no problem.
Okay, perfect. So yeah, I'd say then we close this discussion round. Thanks a lot for the presentation and also answering all the questions. And then I would say we go over to the second talk, and I would give the word to Mats.
Yes, hi everyone. Thank you very much, Marius, for presenting. And yeah, now to the next speaker, also from a student team, from the TUM Boring student team, is Tobias Jäger. Thanks for joining us. So Tobias is in the TUM Boring team for now almost 1.5 years. His main tasks in the team is operations and sometimes as well mechanical engineering. The TUM Boring team is competing in the Not a Boring competition that is organized by the Not a Boring company that is owned by Elon Musk. And yeah, the competition is challenging students from all around, student teams from all around the world, to build a tunnel boring machine that can bore tunnels faster than a snail could crawl. So that's their kind of slogan for the competition. And the TUM Boring team has already won the 2021 competition so far, and now also this year also came back glorious again from America with winning also this year's Not a Boring competition again. And yeah, Tobias just arrived back here in Munich in April after winning the competition. And today he will share his insights and some deep knowledge from the competition, as well as like the current state of the tunneling industry and market that is closely relevant as well for the Hyperloop and maglev eco environment. So thanks for being here, Tobias. The stage is yours.
Yeah, thank you so much for the introduction. Thank you so much for having me. Just really brief, I'll start by talking about like what TUM Boring is, how we came to be, and like what we do in terms of tunneling. And towards the end, I'll say a few sentences about like the future, where we see ourselves in the tunneling industry, and how we think we can improve it and have an impact on the mobility of the future. So Mats just took the part of the next slide a bit away. So how does it come that this group of students builds a tunnel boring machine and yeah, competes with it in the US? This year it was in Texas. So similar to how TUM Hyperloop originated, there was a competition that was announced by Elon Musk. The first one was announced in July 2020. And the challenge was, yeah, who can dig a tunnel the fastest? The general requirements were, so you have the scales like 30 meters in length at a depth of 1.5 meters with a tunnel diameter of 0.5 meter. And yeah, fueled by the success of the TUM Hyperloop team, another group of students from the Technical University of Munich took that challenge and built a tunnel boring machine for that. And I have a video showing the general how the machine was built. I'm only working with one screen right now. Please react if you don't have the sound. So let's take a look at the TBL. I hope you can hear the sound. Maybe you can give us thumbs up.
Only working halfway the sound, but is it that important or?
Not necessarily. So you don't have sound?
No.
Well, then I can skip through the interesting part. Okay, so here you can see the TVM, it's not animated. Then I would like to go over so in general, our tunnel boring machine, the idea behind it is that it's in a 12-meter long, 40-foot shipping container, which is different from what is generally used in the industry. The main reason for it is just that it was designed from the ground up to be competed with in the US. So obviously there has to be some kind of logistic to transport it, in this case, over the Atlantic Ocean, and building it in a shipping container for that reason makes it just easy, but it comes with a lot of different advantages since when logistic is easy, actually for a large scale tunnel boring machine, the logistics is actually a large chunk of the operating cost because you need like the heavy transport vehicles, you have to close down highways just to transport the cutter head. Obviously the scale is different, but the logistics being easy has a large advantage. Just so you have the scale in mind, our entire machine weighs about 22 tons. Yeah, so it's a piece of heavy machinery. This is what we competed with in 2021, which was the first time that competition came around. And then for the one in 2023, which is the one I'm going to talk about now, there were a few things that had to be changed. So for the new year, there was a new challenge in terms of a new trajectory. In the original competition requirements, there was a winning category for tightest radius, and building a curve in a tunnel is not a trivial challenge. You might be used to like the highway tunnels, which use concrete segments. So these would have to be individual. So building a curve, you also need a guidance system. You kind of need to be able to steer your machine, and you need to know where you are. So those are challenges that have to be solved. And the second one is that the second generation of the motor boring competition was in Texas and not in Las Vegas as the year before, which meant a lot of different geology, mainly changing from dry sandstone to wet clay, which poses a lot of challenges in terms of clogging, as well as that the boring company actually did not provide us with the exact location where we were going to dig, though the area has like different geology formations coming together. So the blue dots, as well as the red dots on this picture, are the places where we got a detailed geology report. And the green dot is then where we actually were allowed to dig for the competition. To solve those challenges, we did a few changes. So in the year before, we used steel pipes, but you can't really do a curve with steel pipes because they don't bend as much. So the option you have is either you build a connector between the pipes that's kind of flexible, or you use flexible pipes itself. We went with the option of going with flexible pipes, which was a huge concern in the beginning because, well, pipes that bend easily might also fold easily in terms that it cracks or it would break. So a large part of our early testing was taking the pipes and putting a lot of buckling force on it to see how they react, and for us to try to get the safety factor as low as possible so we can have thin walls, which is relevant because the competition requirements with a 0.5 meter inner diameter, so they say it's a functional diameter, so it has to be the inner diameter, and having the walls thin makes obviously the outer diameter smaller, and that's relevant because the tunneling time increases with the square of the diameter because it's then always such more volume. So keeping if your goal is to go fast, you have to keep the diameter as low as possible. So in these pictures, you can actually see our pipes on the left side, how they are curving downwards, which was pretty cool to see at the competition. So we managed to be able to dig a curve by having flexible pipes. Now, how do you remove the material from the pipes? This is kind of funny because it's called a vacuum seminar here, and what we used is a big vacuum truck. So we cut the material with the cutter head, which is on the bottom right, and it gets transported into something we call a mixing chamber. So there the salt flows together, which is the one on the bottom left. See if I can, so apply the animation again. So the particles are basically the soil, and that's hooked up to the big truck you can see in the top right, which creates a vacuum and sucks out all the material, so the cutter head can keep digging. With that, we can achieve a material removal rate of about 8 cubic meters a second, which is obviously way more than what we would actually need to have. But as you can also see, it requires a huge truck. There are smaller versions of such vacuums, which actually some of our competitors at the Not a Boring competition attempted to use. We also attempted to use them, but didn't use them at the end of the day because the power they provided is not nearly enough to sustain the vacuum with all the losses from friction as well as imperfections in the tubes for a distance that is any reasonable length. One difference is when you dig a curve, it's not as easy to know where you are. When you dig straight, you can just have a laser that goes straight and you have a target on the other side and you see, oh, I'm deviating a bit up, so let's go a bit more down. We used an IMU. So that basically takes all the small movements you make and adds them over time, which can then tell you where you are. Obviously, the error of that increases over time and actually over length. Also, this is an interesting application because in front where the cutter head is, there's a spinning wheel, so there are lots of vibrations. And the IMU is then trying to add up all those vibrations, which tends to add a huge error. But we mitigated that through software as well as including a vibration sensor in the cutter head. The cutter head is actually one big part of our challenges. So I told you that one huge challenge was the new geology. The cutter head largely stayed the same in terms of max torque and RPM it can do. We changed the cutting tools. Since this time it's not really about breaking stone. It's about like cutting pieces from the soil and trying to have it not clog up the cutter head, which you can see here. So these were actually our tests in Germany, and it doesn't take a tunneling engineer to see that on the left side, there's something wrong. So when the cutter head clogs, we still have the vacuum attached to the back, but there's no more material flowing through. And that is an issue that we had to fix, but we're not so sure how to do it while keeping most of the design we had the same. Coming from the last generation, obviously we couldn't just like increase the diameter by a lot, or like the number of variables we were able to change, we were kind of limited. So our solution to that looks like this. For those of you that, I figure many of you are engineers here, but for those of you that can't do the technical drawings that well, we have the 3D model here. So we built a sleeve made from one piece of steel that goes over the cutter head for a reason. That is, we are trying to put some polymers, some chemicals in the ground to make the clay not sticky anymore. That system is called soil conditioning. And that was quite interesting because we built the entire thing in the US. We shipped our machine without that system, and we spent a month in the US building a supply chain and trying to get all the components to get this to work. So you can see those channels going along the long side of the metal sleeve. This is basically where like liquid, like foam, flows through and goes to the front of the cutter head, where it is injected in the ground to then make it less sticky. And that then looks like this. In my opinion, this looks pretty neat with the foam coming out of the front of the cutter head. And this worked pretty well. So this is then how it looked at the competition with new cutting tools, and you can see the sleeve on the outside. Obviously, if you just remember from just a couple minutes ago, the picture, so this is before digging, but this actually resulted in us not having clothing. So all the 4 quarters you see where the soil can move through stayed largely empty, which was pretty cool. Now just a few impressions of how we worked. This is actually a picture of our test site. So obviously spending about a month in the US testing our systems, we had to have a test site. And what's interesting about this picture is you see our machine on a hill and it's angled downwards. Whereas in this picture, it's actually horizontal on the ground. So in the beginning, we thought since everything in the machine is horizontal, we thought we would have to put the machine up to be able to dig down and then dig back up again to do the curve. But due to testing, we realized that the weight of the cutter head and the ability of the polymer pipes are flexible enough for the weight of the cutter head to pull the pipes down to be able to put the container horizontally on the ground directly with a crane and start digging downwards, which is incredibly neat because this allows for an operation which just consists of you have a machine, it can be transported to anywhere where on the continent or in the world. It arrives on a truck, you just need a crane, you unload it, put it on the ground, and you can start digging. You have to plug in some cables before and the control panel, which is this. But apart from that, it's basically just a put the container down and start digging system. Our machine sadly cannot yet be operated fully autonomous or by some AI. We have some brains behind that. So what you see here on both pictures is actually the control panel. So this is how it looks like to steer a tunnel boring machine. And since we are all millennials, we have a touch screen there, which works pretty cool. So this is then us after our cutter head surfacing. So we put the container down, we dig down, and we steer up. And that means that at some point the cutter head comes back out of the ground. And this is where it came out. And here you can actually see that it is not clogged. So obviously there is some soil, but you can clearly see the openings, which is what you want to see. Now, so this is what we did in the US. Let's talk about mobility. I'll take a step back. So a bit more than 100 years ago, humankind learned to move. With the introduction of the car, some people actually go as far as saying the car created the modern middle class as we know it. But today we are at a position where we are once again not really able to move because we have congestion. We have congestion in the cities, we stay in traffic jams. This is actually one of the reasons I'm currently still in Garching at the university. I did not drive home earlier because I don't really see the reason of spending like 1 hour in traffic jam when the traffic at night after the seminar, when I go home, is just about 25 minutes. So it is obvious some solution needs to be created, some innovation has to happen. And generally, there are two concepts. We need space to move things, to move people. Ideally, we would like to use the space where you have the sun and you have some plants for people, because that's what makes a livable city. So you can go up. There are plenty of examples for like flight taxis, like Lilium. Though, now that's my personal opinion, there are some valid topics like noise pollution. If you have been to New York City, you always hear the helicopters. I think many people object to that. So the alternative solution going up is going down. And that is what we are actually doing. So in tunneling, our goal is to be able to bring down the cost of how it takes to build something underground to create space for a system that enables mobility. Now, we are not the ones creating that system. For that, we have from Hyperloop, we just had, we have Eurotube, we have different companies who have their concepts that need some space to work somewhere, but we're really trying to enable that innovation to give it the space to exist. Now, there's a large difference because we take half a meter diameter. That doesn't fit a car, that doesn't fit a human. But the idea in what we're doing is, for one, is we would like to scale up, but building something in small actually has a huge advantage, which is you can test new technologies relatively resource efficiently, and then try to scale it up and use the knowledge you gain to build something on a scale that is more usable to general society. Apart from mobility, what we actually also could do more with the diameter we do right now. So building half a meter diameter is not just, oh, we're starting small to have something easy. It is actually a diameter that is also competitive in the industry, just not for transportation of humans, but for example, for transportation of energy. So you could use heating it for heating pipes. You can use it for glass fiber. And the neat thing with our concept would be that whereas today, I'm sure wherever you live, you often see like there's a street being torn up to like pipes or cables inside. And then you have to close it up, and then you have to bring new concrete and close it up again. With our concept, we could just simply have a hole that's 12 meters long, put the machine inside, and have it dig the tunnel without having to open up the entire surface of the street, which might bring cost advantages, but also saves you a lot of stress in the traffic jams that you don't have to endure then when coming home. In terms of innovations in tunneling, I want to point out some topics where innovation is being done, where research is being done, where things are interesting. So one topic that one might not expect that is interesting, but I want to point out is one huge time wasting factor in large tunneling is actually that you don't know when your cutting tools are breaking. So, well, you realize they're broken because you have to increase the torque. The cutter head is not running as good anymore, but there's no like active wear monitoring. So if you're interested in research, this might be a topic that's well for tunneling, to kind of maybe include some sensors in there, or build some steering system that, seeing from the amount of torque it takes, realize that something is wrong and can adjust that, which goes hand in hand with automation. You can see that our machine is steered by hand, but for industry standards, what we do is actually quite automized. A typical tunnel boring machine has someone driving it like a car, and he looks at the screen, he sees the torque, he sees the RPM, or she. And from that, they just say, okay, I am increasing torque now because the geology here needs that. But it all goes by intuition by one person. It's not automized, which is a huge point where progress can be made to increase longevity of the tunnel boring machine itself, and to possibly increase tunneling speed, therefore bringing costs down. Yeah, I'll be happy if you have any questions. I'm aware there were no like deep, specific details as in the talk before, but if you're looking for any number or any approach we took, sure, let me know and I'll try to answer it.
Yes, thank you very much. There actually are some questions, so you probably also have to go into the details for us. So the first question is, do you think the suction excavator is a long-term solution for big scale diameters? Looking at companies such as Herrenknecht, they do not use that technique to remove the soil. Why did you go with that solution?
Yes, so I start with why did we go for suction excavator? We had a conveyor belt system in the beginning, but we were afraid with the new geology having a hugely high water content, and our conveyor belts were in a way where they're pretty flat. So to avoid like spillage to the side and making all our internals of our machine dirty, we went for a closed suction excavator system. Such a system is actually relatively standard for small tunneling applications. So if you want to have small holes, that is actually the way to go. But as you said, yes, if you scale up, there is a problem with one is increasing the diameter, and you have a small truck at the end. For once, you would have to empty it like every few centimeters because you create so much soil with a large diameter, and obviously it creates a problem with the pressure difference. So the way for large machines like Herrenknecht is mostly to go with. So there's actually two standards that I'm aware of. One is a conveyor belt, but you build it in a way that it is really like sloped. And the second one that's actually being used is you can have like small carts driving in and out, removing the soil, but for obvious reasons that is way more inefficient than a conveyor belt system, which can bring out the soil in a continuous cycle.
Thank you very much. Then the next question is, why didn't you look into liquid membranes as other teams did? Looking at the big scale tunneling industry, this method offers quite some advantages when sealing the system, since no big pipes or welding is needed. What solution do you have in mind for the next competition?
So with liquid membrane, you mean liquid tunnel liner? Like, so it's like extruding a polymer for the wall of the tunnel?
Maybe Danny, you could directly answer that
exactly.
question.
That's the idea. We used to use liquid membranes to prevent the tunneling of collapsing.
So what our goal was from the beginning to build a tunnel boring machine that is fast and obviously also one that works. And for that, we started to go with solutions that are reliable and known also in the industry. So I think what it comes down to is that the way we build a tunnel is called pipe jacking. That means you grab a physical pipe and you push it forward. And when you already have a pipe in there, like we had with the steel pipes in Las Vegas or with the polymer pipes in Texas, they are sturdy enough for any soil load there is. So having that system, there would be no need for any other system to prevent tunnel collapse. Does that answer the question?
Yeah, I think so. Pretty much. So it's basically a question of the concept, which is directly linked to choosing a stiff pipe, let's say, or a continuous membrane.
Yeah.
Nice. Then I would have one last question as well. So what do you think, in your personal opinion, what did you do a lot better compared to the other competing teams? Was your concept just the best, or did you just had luck? And did they also use like steel tubes, or did they also use like these flexible tubes? Was there like a big advantage of choosing that, or some other major difference that like made you in the end the winner?
Yeah, just for interest, is someone from Swiss Loop Tunneling here who was in the US? I think that is no, I just see Swiss Loop on their screen. So what we did better, it comes down pretty much to testing. So when you go to that competition, or if you would have been there, what you would have realized that basically most other teams had the problems that some integration of components didn't work, or they're not used to having their machine built up. So our goal was always to be reliable, to have the machine working, because a tunnel boring machine is a hugely complicated and complex machine, because there's so many small components that have to work together. And when one small component fails, the entire system is down. So to ensure that, what we did is, so the competition was 2nd of April. It might be 1st of April. We arrived in the US end of February. So we spent a long time, basically like 1 to 2 kilometers away from the end of the day where the competition site were. And we just tested and tested and tested. We worked every day. We tried to dig as much tunnel as possible before to know our machine works and to know where our problems arise. And you can see from the other teams that they did not have that experience, but you can't blame them. It's hugely expensive to test a tunnel boring machine. You have to have a ground somewhere for it. You need some machinery to then, at the end of the day, fill the hole back up. You need to transport the machine. But so what we did better is testing to ensure reliability, that our machine actually does what it's supposed to.
I mean, this also means you have to be done with the design quite early, right? So did you just set the deadline quite early, or did you just then do the design in progress while you were still testing? Or
I mean, so for the general design, the advantage was that we had a machine from the year before, but the other teams did as well. With having the design finished early, the soil conditioning system we implemented, which was basically the biggest factor of us being able to dig for more than just the tiny bit of a few meters, because then our cutout would just stop clogging. We built that in the US. So it's not that we had our machine finished 5 months before the competition, but it doesn't take the whole machine to be completed in a competition state to actually be able to test it. Obviously, you can test components, single components, but the key takeaway, and maybe the one thing for your project that I would recommend you do, is actually, like, even if all your singular components work, put them together and see that the entire thing works, even if some parts are not done yet. Like, if the cutter sleeve is not on it, you can still see that the cutter spins and the steering works.
sure, yeah, nice. Yeah, thank you very much for the insight. And yeah, so then we don't have any more questions, I guess. So we're at the end of today's seminar. I hope, Tobias, thank you very much for being here today, and I hope you get home in time without a lot of traffic. And then I'm handing back to Daniel, who's closing the seminar then.
Thanks, Mats. Thanks, Tobias, for the very nice talk. With this said, we also arrived to the last session of the season. With this said, we will be coming back in the fall semester, most probably with new insights into various Hyperloop topics. So with this said, I wanted to thank, in the name of all organizing organizations, Swiss Loop, Institute for Hyperloop Technologies, and TUM Hyperloop for the involvement this year, and also the audience, which week by week may make also this seminar more vivid. So with this said, stay tuned, and we hope you got a bit more home from what Hyperloop is and where, let's say, all these technologies is moving forward. And yeah, as soon as we have new dates, we will let you know, and we're looking forward to your presence in the fall semester.